Hello and welcome to the second video of the M3 chapter Dynamics. On the screen, a quick exam question to review the previous video. A car of mass 800 kilograms moves along a horizontal straight road. At time t seconds, the resultant force acting on the car has magnitude this, acting in the direction of the motion of the car. When t is equal to 0, the car is at rest. So here we have our boundary condition, and here we have our variable force dependent upon time. Show that the speed of the car approaches a limiting value as t increases, and find this value. So we have a variable force here. Let me write that down. 48,000 t plus 2 to the minus 2. We also know F is equal to ma, where we're going to have 800 for the mass, and for a we're going to write that as dv by dt, because the force is given in terms of time. So we can replace the force here with that expression, and then separate our variables and integrate. So we'll have 48,000 t plus 2 to the minus 2 dt, integrate that, and 800 dv, integrate that. To make it a bit easier, I should divide both sides by 800. We get a 1 there, and we get 60 here. Then integrating gives t plus 2 to the minus 1 divided by minus 1, so we get minus 60 there. We get v, a constant of integration. Now we know that when t is equal to 0, the car is at rest, so v is equal to 0 when t is equal to 0. We can put in those boundary conditions. We get minus 60, 2 to the minus 1 is equal to 0 plus c. 2 to the minus 1 is just a half, so half of 60 is 30, so c is minus 30, which gives us minus 60 t plus 2 to the minus 1 is equal to v minus 30, or if I rearrange that, we get v is equal to 30 minus 60 over t plus 2. The question wants us to find the speed of the car as t increases and it approaches a limiting value. And we can see that this happens because the t here is in the denominator, so as t increases, the 2 becomes less important. This number on the bottom of the fraction increases, so the fraction as a whole decreases as this becomes big enough. This becomes effectively 0, and the limiting value is just this value here, 30. So as t tends to infinity, 60 over t plus 2 tends to 0, therefore v tends to 30 meters per second. In this video, we are going to know and use Newton's law of gravitation, which is a little bit different from what we've done so far, but it is connected to what we used in the first video, the calculus element here. But before we get into that, I need to make a very clear distinction, because we have used g quite a lot in this course and in previous mechanics courses, but now we also need to use capital G, and there's a big difference between these two. Little g is the amount of acceleration on the surface of the Earth due to gravity. Now I should be clear here because I have called this by the wrong name in previous videos. I can remember at least once I've called this the gravitational constant, and that was not correct. It's the acceleration due to gravity. That distinction becomes much more important in this video because capital G is the gravitational constant, the universal gravitational constant. So a quick word on these two. Little g is not a true constant. Although we tend to use 9.8 in this course, g is approximately 9.8 meters per second squared, there's the acceleration element. This is not actually constant. It's the acceleration due to gravity on the surface of the Earth, but that depends on where you are on the surface of the Earth. If you're at sea level, it's approximately 9.81. But if you go to the very top of the highest point of Mount Everest, it reduces to approximately 9.77 because you're a little bit further away from the center of the Earth. and if you go down into the deepest ocean, it would increase slightly. So this is the value of the acceleration due to gravity on the surface of the Earth. It's not a true constant, although 9.8 is a good approximation, and to two significant figures, it will be 9.8 wherever you are on the surface of the Earth. As compared to that, capital G is a true constant. This is the universal gravitational constant, and it's the constant that is used in Newton's law of gravitation. Newton's law of gravitation is about the force of attraction between two masses, m1 and m2. And what Newton found was that as the masses involved increase, then the force of attraction between them also increases. And as the distance between them increases, as they get further away from each other, the force of attraction decreases. So the statement of proportionality is this: the force of attraction due to gravity is proportional to the product of the two masses divided by the square of the distance between them. And this is where our universal gravitational constant comes in, because it's the constant of proportionality for this statement, which becomes this. And it might seem, just by looking at this formula here, that everyday objects should have quite a large force of attraction due to gravity. If we have two masses that are quite big, maybe a car and a house, they've got quite a small distance between them, we might end up with these things being attracted by gravity. But we need to take into account the universal gravitational constant. And we know that if you leave two cars on a road next to each other, they don't just slowly draw each other together and collide. It just doesn't happen. This formula is far more useful in situations where one of these two masses is very large, for example the Moon or the Earth. And that's because G is a very, very small number. And we can calculate that using things we know about the Earth. So if we use little g, we can calculate capital G by considering a particle of mass m on the surface of the Earth. Because we know two things now about F. We know F is equal to ma, and we know the gravitational attraction force is equal to G m1 m2 over d squared. So if we combine these two, because we know that mass times a for a particle of mass m on the surface of the Earth gives us mg. We've used that as weight many times before. If this is also equal to this, then we can rearrange and get capital G in terms of little g, which we already know is approximately 9.8. So equating these two things, we get mg on the left is equal to capital G, where one of these two m's is the mass of the Earth, so let me call that me, and the other one is the mass of the particle, little m, this m here. And the distance between them, we need to be careful here. A particle on the surface of the Earth does not have zero distance, because the distance here is measured from the center of one particle to the center of the other particle. So we go from the center of this particle, the center of the Earth, to the particle on the surface of the Earth. So the distance between them is the radius of the Earth. And then we have to square that. And now we can rearrange, and we get capital G, if we cancel those two m's there, is equal to little g times the radius of the Earth squared divided by the mass of the Earth. Now the radius of the Earth squared is obviously a very large number, but it pales in comparison to the mass of the Earth. This is a huge number. We pull up those two numbers. The radius of the Earth is approximately 6.4 times 10 to the 6 meters. Now that's 6 million meters, but the mass of the Earth is approximately 6 times 10 to the 24 kilograms. And you can see as you compare these two, even though this is a huge number, this is still so much bigger. So when we put those in, G is equal to, we know little g is approximately 9.8 times the radius of the Earth, 6.4 times 10 to the 6. Even when we square that, it still doesn't come close to 6 times 10 to the 24. That is a really big number. And when you do that, we get the answer for capital G as approximately 6.67 times 10 to the power of minus 11. That's given to 3 significant figures, and you can see some rather unusual units here. We've got meters cubed here, that comes from meters squared from the radius, and there's also a meters involved in g, which is an acceleration, so that's meters per second, so that gives us the third meter here, and also the 2 seconds here, and then we have the kilograms on the bottom, so that gives us the per kilogram as well. So unusual units, tiny number, 10 to the minus 11, so this is our gravitational constant. And now we know what this is, we can go back to the formula here, and we can see why this is not something we need to worry about for everyday objects. Two particles of masses 3 kilograms and 4 kilograms, they're just 2 centimeters apart. That's a very small distance. And when you square that, that becomes a really small. When you divide by something really small, you would normally expect a really big answer. But we're going to calculate the magnitude of the gravitational force between them and find that it's really tiny, because this capital G is going to overwhelm what might seem like a large number that should come out of this small distance here. So let's go ahead and do it. F is equal to capital G, 6.67, times 10 to the minus 11, times mass 1, 3, times mass 2, 4, divided by, in meters, 0.02 squared. And that gives us the answer 2 times 10 to the minus 6 newtons. And you could make the comment that although it's tiny, it's not zero. These two are being attracted towards one another with a force. And they are, but it's so very tiny that any amount of resistive forces, which we always have on the surface of the Earth, you just can't get rid of resistive forces completely. Any amount of resistive force is going to completely overwhelm this tiny gravitational attraction force. And if you try and make this number even smaller and these numbers even bigger to try and get something that might actually move due to gravitational attraction on the surface of the Earth, you hit a very practical limit where you can't get things that are so very massive that close together, because like we said previously, the distance here is not the distance between the surfaces of the objects, but the distance between the centers of the objects. And generally speaking, as you increase the mass of an object, you're eventually going to have to increase its size, because we have a limit on the density available to us. So there's a justification for what you already know. The force of gravitational attraction between everyday objects on the surface of the Earth is negligible. It can be pretty much ignored in all cases. However, if we have an example with a satellite orbiting the Earth, then obviously gravitational attraction becomes very important. If you're dealing with a question like that, then you should notice that when we use this formula here, we're making the force dependent upon distance, not time. So when we combine this with our F equals ma to solve a problem using calculus, you should use a is equal to v dv by dx, not dv by dt. And then we can apply all of the work that we did in the previous video using this as the force involved. So here is an example of this. Above the Earth's surface, the magnitude of the force on a particle due to the Earth's gravitational force is inversely proportional to the square of the distance of the particle from the center of the Earth. We already know that. That's the d squared here on the bottom of this formula. The acceleration due to gravity on the surface of the Earth is little g. We already know that as well. And the Earth can be modelled as a sphere of radius r. A particle p of mass m is a distance x minus r above the surface of the Earth, where x is greater than or equal to r. So for example, if x is equal to r, then r minus r, the radius of the Earth, is 0. So it's on the surface, but it's still a distance of r away from the center of the Earth. As it goes above the Earth's surface, let's say it's 50 meters above the surface of the Earth, then x minus r is 50, therefore x is 50 meters plus the radius of the Earth. And the question we're being asked is, prove that the magnitude of the gravitational force acting on P is this. Now we're going to be a little bit sneaky here and use something that we've already done on a previous screen, because we're going to start with F is equal to g m1 m2 over d squared and go back and consider what we found for capital G, and that is that capital G can be written in terms of little g in this way here. So if we use this expression with the radius of the Earth and the mass of the Earth, we know that g is equal to little g radius of the Earth squared over mass of the Earth. And just before we use that, let me comment that you can see here why little g is not a true constant, because although the mass of the Earth is a constant, the radius of the Earth changes depending on where you are on the surface, because it's not a true sphere. You can go higher up and you can go lower down on the surface of the Earth. So as you increase your altitude on the surface of the Earth, this number goes up, and if capital G is a true constant, then this number must go down to compensate. So if we put this expression in for capital G here, we get little g r e squared m1, where m1 is the mass of the Earth, times m2, where m2 is the mass of the particle, divided by the mass of the Earth from this expression here, but also d squared from the main expression, where d squared is the distance between these two particles, or more to the point, the center of these two particles. So that's x, because x minus r is the distance above the surface of the Earth, so when we add on the radius as well, we get just x. And we have to square that. Then we see that the mass of the Earth cancels top and bottom, and the radius that I've called RE here is just called r here, the radius of the Earth. So that gives us g r squared m over x squared, which should have rearranged to mg r squared over x squared to match the question. For a question like this, if you hadn't remembered this, then you would have to go through the process that we had on the previous screen in order to get this, in order to put it in here and get this. Part B. A spacecraft S is fired vertically upwards from the surface of the Earth when it is at a height 2r above the surface of the Earth. So at that point x would be 2r plus r, so 3r. Let me make a note of that. Its speed is 1/2 root gr. So there's a boundary condition for us if we need that. Assuming that air resistance can be ignored and that the rocket's engine is turned off immediately after the rocket is fired, find in terms of g and r the speed with which S was fired. So this is a very unrealistic situation. I'm sure you know that when a rocket engine is fired into space, it is not turned off immediately, it burns for quite a long time, and at those sorts of speeds, air resistance certainly cannot be ignored. But we're not worried about being realistic here, we're just trying to apply what we know to a very simple model. So we're trying to find the speed with which S was fired, and we know from part A that the force involved is mg r squared over x squared, and we also know from Newton's second law that it has to equal ma, where a we can change into v dv by dx. So the resultant force there is mg r squared over x squared, and that's the only force acting because the rocket's engine was turned off immediately after it was fired. But we should be careful with our directions here, because the force is acting down towards the centre of the Earth, which is in the opposite direction to its displacement from the centre of the Earth. So we should have a little negative in here. Now we do what we did in our previous video, we separate the variables and integrate. So we've got minus mg r squared, all of which is one giant constant, integral 1 over x squared dx must equal m integral v dv. Now I can cancel the m's and integrate. The left hand side, the negative becomes positive when we integrate. We get g r squared over x is equal to v squared over 2 plus c. Now we do have boundary conditions to calculate c. We know that when the height is 2r, therefore x is 3r, then the speed is this. So if we put that in, we get g r squared over 3r is equal to 1/2 root gr squared is a quarter gr, and then it's also divided by 2, so you get 1/8 of gr plus c. The r squared and the r there cancels. We get gr over 3 minus gr over 8 is equal to c. 1/3 minus 1/8 is 5/24. Now we can put that back into the equation. So we get gr squared over x is equal to v squared over 2 plus 5gr over 24. From here we can find the speed with which s was fired by putting x is equal to the radius of the Earth, r, i.e. it's on the surface. So at x is equal to r, we get gr squared over r is equal to v squared over 2 plus 5gr over 24. That cancels with that. We get gr minus 5/24 of gr, 19 over 24 gr on the left is equal to v squared over 2 on the right. That gives me v squared is equal to 19 over 12 gr, so v is equal to the square root of 19 over 12 gr, which is not the nicest looking answer in the world, but here we have the answer to the question. Finishing with an exam question. A rocket is fired vertically upwards with speed U from a point on the Earth's surface. The rocket is modelled as a particle p of constant mass m, and the Earth as a fixed sphere of radius r, at a distance x from the centre of the Earth. The speed of p is v. The only force acting on p is directed towards the centre of the Earth and has magnitude this, where c is a constant. Show that v squared is equal to this thing here. This is quite similar to what we've just done, except that they're telling us this instead of asking us to work it out. So we're being told straight away that the force involved, the only force involved, is cm over x squared. We know F is equal to ma, where little m here is the mass of the rocket, particle p, and they're very clear that the force is acting downwards towards the centre of the Earth, which is in the opposite direction to the way it's moving. So let's put a minus cm over x squared is equal to mv dv by dx here. Now it's very similar to the previous example. Separate our variables, minus cm integral 1 over x squared dx is equal to m integral v dv, and again I forgot to cancel the m's, let's do that now. So we get c over x is equal to v squared over 2 plus a constant, which I normally call c, let's call that k. Our boundary condition, the rocket is fired vertically upwards with speed U from a point on the Earth's surface, where x is equal to r, the radius of the Earth. So our boundary condition, where x is equal to r, v is equal to U. So we get c over r is equal to u squared over 2 plus k. So k is equal to c over r minus u squared over 2. Putting that back in, we get c over x is equal to v squared over 2 plus c over r minus u squared over 2. Now I just need to rearrange into the format they want, so I'm going to multiply everything by 2 to get v squared and throw everything else on the other side. So v squared is equal to 2c over x minus 2c over r plus u squared. Now I can factorise out 2c from the first two terms and put u in front just to match what they've got. U squared plus 2c times 1 over x minus 1 over r. And there we go. A lot of that was using work we did in the previous video, but you must remember that law of gravitation, F is equal to capital G, mass 1, mass 2, divided by d squared. I hope that's enough now for you to have a go at the questions in exercise 3b, and maybe I'll see you for something very different, simple harmonic motion, in the next video.